Hello friends, welcome in the lecture series of Pericyclic reactions CHO-250. Let's continue the analysis of electrocyclic reaction by frontier molecular orbital method, that is FMO method. Let's continue the FMO method for 4n plus 2 pi electron system. Now in the 4n plus 2 pi electron system, this is 4n plus 2, that is 6 pi electron, 4n plus 2 pi electron system. So ring closing reaction of this 4n plus 2 pi electron system is represented by general reaction here. In this case, we have written all the we draw here all the molecular orbitals psi1, psi2, psi3, psi4 star, psi5 star, psi6 star, and derived all the symmetries. Okay, all the symmetries here. So symmetries: M symmetry for first orbital, M C2 symmetry for second, M for another, C2 for psi4 star, M for psi5 star, and for psi6 star C2 symmetry is present. So this is symmetrical representation. Now in frontier molecular orbital, the electron distribution is important, and from that we can find out highest occupied molecular orbital and lowest unoccupied molecular orbital. So HOMO and LUMO, these are two important concepts in frontier molecular orbital method, FMO method. In FMO method, the electron distribution, so here total 4n plus 2, total 6 pi electrons are involved in the reaction. So 6 electrons distributed in the manner, 2 electrons in the first orbital. Each orbital, like atomic orbital, it has capacity of 2 electrons only. So 2 electrons, so next goes to higher energy orbital, 4 electrons, and then again 2 electrons. So total 6 electrons are there. In the ground state, this is ground state. So the ground state representation, ground state. In the ground state, there is no excitation. The orbitals filled as the lowest energy field first, then higher energy, then again higher energy. So in this manner, by using the Pauli's exclusion principle, Gauss principle, Hund's rule, so all the rules for filling these orbitals by electron applicable like atomic orbitals, as all the rules for atomic orbitals which are applicable here in this molecular orbital, psi1, psi2, psi3, psi4 star, psi5 star, psi6 star. So all these are molecular orbitals. So in this case, ground state distribution of electrons is this. So we have to decide HOMO and LUMO. Now highest occupied is the psi3, is the highest occupied molecular orbital, and this is lowest unoccupied molecular orbital. Lowest unoccupied molecular orbital. So HOMO is the important case in electrocyclic reaction. So we have to observe the symmetries of HOMO. So HOMO, in this case, HOMO is HOMO, psi3 is HOMO, having which symmetry for psi3? Symmetry is M symmetry, having M symmetry. So M symmetry represented in this way. So this is M symmetry, plus, plus, minus, minus. So in ring closing, when the M symmetry is there, which rotation required? So rotation required here, this clockwise, this anti-clockwise. One clockwise, another anti-clockwise, then it leads to bonding overlap. So here bonding overlap occurs only when we rotate one clockwise, another anti-clockwise, so that this type of overlap, and which is bonding overlap or allowed overlap. Bonding overlap is there. So by this rotatory motion, which motion required here? This rotatory motion. So here this rotatory motion required for this this transformation. Now HOMO is cyclic. Which is this HOMO? This is ground state HOMO. Hence, if ground state HOMO, if we consider, then the reaction is thermally allowed. So this reaction, or we say conversion of 135 hexatriene to 1,3 cyclohexadiene. Cyclohexadiene, 135 hexatriene to cyclohexadiene. The conversion of 135 hexatriene to 1,3 cyclohexadiene by thermal mode of activation. allowed by this rotatory motion. This rotatory motion. This reaction is not allowed by con-rotatory motion because the symmetry of HOMO is M symmetry, and when there is M symmetry, the bonding overlap occurs only when we apply this rotatory motion. So here we applied this rotatory motion. This rotatory motion leads to the bonding overlap. So this conversion by thermal mode of activation, that is by using ground state HOMO, allowed by this rotatory motion. Let's see the photochemical mode of activation. How photochemical mode of activation we use here and which rotation is required here. So in this case, how photochemical? When we use photochemical mode. Photochemical mode, then see Psi1, this is for Psi2, Psi3, Psi4 star, Psi5 star and Psi6 star. Okay, so 6 molecular orbitals. What happens? 2 electrons are in the ground state. Again 2 electrons, but last electron, outer orbital electron, one of the electron by excitation energy given by photon, one of the electron from this goes to higher excited state. Now which is occupied? This is last occupied. Okay, highest occupied. So this is HOMO now. Which is that? This is HOMO now. HOMO is what? Psi4 star is HOMO. So Psi4 star is HOMO, and this LUMO changes to Psi5 star. So another LUMO, and this is HOMO, highest occupied molecular orbital. Now this is highest occupied molecular orbital. So Psi4 star is the highest occupied molecular orbital. So in excited state HOMO, that is by photochemical activation. When we considering the excited state HOMO, when the activation is by photochemical mode. Now by photochemical mode, the activation by photons in excited state HOMO is Psi4 star is excited state HOMO having which symmetry? So Psi4 star having C2 symmetry. So C2 symmetry is shown in this manner. These are the end carbon atoms which taking part in the bonding. So C2 symmetry represented in this manner. So this is C2 symmetry. You know that C2 symmetry is represented in this way. So when C2 symmetry is there, we want bonding orbital. Then this rotated clockwise, another rotated clockwise also, or it may be anti-clockwise, counterclockwise we can rotate. So by rotating this, we reach to the bonding orbital. So when this rotated, it plus minus. When this one rotated, plus minus. Then we have bonding overlap is there. So if excited state HOMO is Psi4 star having C2 symmetry, then this reaction is allowed by con-rotatory motion, not by disrotatory motion. Disrotatory motion, this reaction is symmetry forbidden, but by con-rotatory motion, the conversion of 135 hexatriene to 13 cyclohexadiene is allowed by photochemical activation by con-rotatory motion. So con-rotatory motion. So first identify question, and by identifying question write the answer, but the way of writing answer is same here. Way of writing answer is same, and you have to draw all the orbitals, find out the HOMO, whether it is ground state HOMO or excited state HOMO, and by finding which HOMO is there, find out the symmetry of that particular HOMO, and from that symmetry, if M symmetry is there, then that particular reaction is allowed by thermal mode of activation, is allowed by disrotatory motion, and if C2 symmetry is present, then that particular reaction allowed by conrotatory motion. So C2 symmetry always associated with conrotatory motion, M symmetry always associated with disrotatory motion. So this is about frontier molecular orbital method. Before that we have shown the correlation diagram method, in which correlation diagram method, frontier molecular orbital method for 4n pi electron system, 4n plus 2 pi electron system. So this system we have shown how to identify the symmetries, M symmetry, C2 symmetry, how to draw the orbital, molecular orbitals. So for reactant and product both we have drawn this orbital for all the molecular orbitals. So this is about frontier molecular orbital method. FMO method for electrocyclic reaction. So this is about electrocyclic reaction. First topic of the pericyclic reaction. First type of pericyclic reaction, and analysis of this electrocyclic reaction by two methods. We have shown two methods for the analysis of analysis by two methods. Okay. So what we have shown, what we discussed, what we studied, that pericyclic reaction. So in the first we define the pericyclic reaction. So definition of pericyclic reaction which involves cyclic shift of electron. Such reaction, concerted cyclic shift of electron, such reactions are pericyclic reactions. So types of pericyclic reaction. Second, we shown types of pericyclic reaction. Which are the types of pericyclic reaction? There are total 4 types of pericyclic reaction. Electrocyclic reaction, second cycloaddition reaction, third reaction is a sigmatropic rearrangements, and 4 group transfer reaction. So these are the 4 types of pericyclic reactions: electrocyclic, cycloaddition, sigmatropic, and group transfer reaction. So these 4 types of reactions, and then analysis of these 4 types of reactions. Analysis can be done by using 4 methods. So correlation diagram method, second FMO method, third Woodward-Hoffmann rules. There are certain rules to and fourth method is the HM method, that is Huckel-Mobius method. But out of which for first year only 2 methods are there for analysis, and we saw the analysis of electrocyclic reaction by these 2 methods. Correlation diagram, in which we draw the orbitals of reactant as well as orbital of product, and correlate the same symmetry orbital. If ground state orbital correlated with ground state orbital, then that reaction is thermally allowed. If first excited state of reactant correlated with first excited state of product, then that reaction is photochemically allowed. So ground state and excited state gives the thermal allowed or photochemical allowed reaction. So this is correlation, and in frontier molecular orbital we observe the symmetry of highest occupied molecular orbital, HOMO, and from that symmetry we decide whether that reaction by thermal mode of activation is it allowed disrotatory motion or by conrotatory motion, and photochemical activated reaction whether it is allowed whether it is allowed by disrotatory motion or conrotatory motion. So by using these methods we have analyzed the electrocyclic reaction. So from that, general selection rules are here, that is 4n electron system by thermal mode of activation it is allowed by conrotatory motion. By conrotatory motion, and we know that conrotatory motion is always associated with C2 symmetry, so that we can obtain bonding molecular orbital overlap. That in order to obtain bonding overlap, there must be C2 symmetry associated with con-rotatory motion. By same system, 4n pi electron system, but by photochemical mode of activation, the rotation changes and also symmetry changes. So symmetry. So this is about 4n electron system. Now 4n plus 2 pi electron system. Now this system, when activated by thermal mode of activation, for bonding overlap to occur, it is allowed by photochemical mode of activation, and when photochemical mode of activation is there, it is allowed by this rotatory motion. It is allowed by thermal mode of activation. By thermal, when 4n plus 2 pi electron system is allowed by thermal mode of activation, then this rotatory motion is there, and when this rotatory motion, symmetry is there, and by photochemical mode of activation, same reaction, it allowed by con-rotatory motion and C2 symmetry is there. So opposite results are obtained in case of 4n pi electron system and 4n plus 2 pi electron system. So these are selection rules, important selection rules, and in these selection rules, also one important point, that con-rotatory motion and this rotatory motion. Remember these points also, con-rotatory motion and this rotatory motion. In con-rotatory motion, what could happen? Both the orbitals rotated either clockwise or anti-clockwise. Means if both rotated clockwise, we say it is a con-rotatory motion. If both rotated anti-clockwise, we say it is a dis-rotatory. Both rotated anti-clockwise, we say con-rotatory motion. So clockwise or either anti-clockwise gives the con-rotatory motion. Then dis-rotatory motion, in which one orbital, dis-rotatory motion or dis-rotatory motion here, this one orbital rotated clockwise, and another orbital rotated anti-clockwise. One rotated clockwise, one rotated anti-clockwise. So this is this rotatory motion, con-rotatory motion. So this is the summary of electrocyclic reactions. First type of pericyclic reaction, 4n pi electron system, thermal mode of activation, con-rotatory. Remember this. Remember these all rules, selection rules, because in pericyclic chemistry, in pericyclic reactions, you know the results first before solving your problem, because these selection rules gives us results very easily by just observing reaction. By only observing the reaction, you can say that this reaction is thermally allowed or photochemically allowed. So by using these selection rules, so remember these selection rules, 4n system, thermal mode of activation by con-rotatory motion and C2 symmetry is there. Photochemical mode of activation, dis-rotatory motion is allowed and symmetry is there. 4n plus 2 pi electron system by thermal mode of activation allowed by dis-rotatory motion and symmetry is there. Photochemical mode of activation, this system by con-rotatory motion, and it is associated with C2 symmetry. Con-rotatory motion is both orbital rotating clockwise or anti-clockwise, and in this rotatory motion, one rotated clockwise, another rotated anti-clockwise. So this is about electrocyclic reaction. In the next lecture, we have to see the cycloaddition reaction, analysis of cycloaddition reaction by two methods, that is correlation diagram method and frontier molecular orbital method. Okay. So this is about electrocyclic reaction. Thank you.